All right, well, welcome back. So in the last video, we just finished up the last bit of the applications of integration that we were mainly focusing on. Mainly, last two that we were having a look at were the arc length. So we learned about how to use Riemann sums to actually calculate the length between functions using the distance formula. As well, we also had a look at how to calculate the surface area of revolution. So this is by using cones as a way for us to calculate the area, surface area, which is related to the arc length formula. Um, but anyways, so we also had a look at an improper integral example, typical one, which is called Gabriel's horn. So we saw that the volume would actually converge to the value pi, but the surface area actually diverges. All right. So as I mentioned in the last video, we are going to be moving on to the next chapter, which is going to be on ordinary differential equations. So a differential equation is an equation that contains the derivatives of one or more known functions. So for example, in general, you could have, let's say, maybe like y prime, y to the n plus y n minus 1 plus so on, all the way to you have y prime and then y, and that's equal to some function, let's say f of x here. That is called a differential equation. Basically, you know what the variables are that you're trying to solve for. Well, you know the independent variables, but you don't know what the dependent variable is. So you don't know what the y is, but you know what the x's are. So that's a differential equation because we're using the derivatives of the function to be able to obtain the function y here. So because so we're going to be having a look at a couple of cases of differential equations. One of them, first of all, is going to be called the separable differential equations. The second one is going to be the linear differential equations. And then a little side track here, we're going to talk a little bit of reduction of order, and then we're going to talk about the homogeneous differential equations here. Okay, so let's have a look at the separable differential equations first. So a separable differential equation is a first order differential equation. So by order, we mean that, well, what is the order of the derivative? When we say the first derivative, it's going to mean the first order derivative. So meaning that if we say the nth order derivative or nth order, we mean the nth derivative of the function. Okay. So if the function dy over dx can be factored into as a function of f of x and another function of y. So let's say we have a function of x and y. Then this can actually be broken up to g of x and h and y into two different separate equations here or functions here. So in this case, if dy over dx can be written as a factor of x times another function of y, a function of x times a function of y, then that means, well, dy over dx is equal to g of x times f of y. So we'll write it this way. So the name separable comes from the fact that the expression on the right-hand side can be written as a function of x and a function of y. So for another case now, if f of y does not equal to 0, and we're going to let h of y be 1 over fy. So then that means here, dy over dx then becomes g of x divided by h of y. All right. So in order to solve for this differential equation, we want to write it in the differential form. So what I mean by differential form is that, well, I'm going to multiply both sides by the function h of y. So on the left-hand side, I'll have the h of y here. And on the other hand, I'm going to multiply the dx, bring it to the other side. So I'm going to multiply both sides by dx here. All right. So when I do that, what I get is that, well, h of y, we have a function of hy by dy here. And we have the g of x dx. So that is what you call a differential form. So all of the y's are now on one side, and now all the x's are on the other side now. So now we want to integrate both sides of the equation, where on the left-hand side, we will integrate with respect to y, and the right-hand side will integrate with respect to x. So what we will get is that, well, if we integrate hy dy, and we have gx dx, then that's going to be some function, let's say h uppercase h of y plus c1. So I'm going to use two different constants here, because if you take the integral on both sides, you'll always end up with a constant here. But I'll talk about that in a second. So on the right-hand side, we'll have g of x plus c2. Now, I'm going to bring the constant c1 all over to the right-hand side. So I'm going to write this as hy is equal to gx, g of x plus c2 minus c1. Now I'm going to because these two are just going to be arbitrary constants, we could just join them together and make them together as one constant. So I'm going to say let c be equal to c2 minus c1. So then that means h of y is equal to g of x plus c. So sometimes it's not easy to actually obtain a function of y. Sometimes it might be in implicit form. Sometimes it might also be in explicit form of a function of y. And we'll see later on why that is. So let's have a look at some examples. Hopefully you get the idea on what to do here. So let's say we want to solve the differential equation dy over dx equal to x squared divided by x squared. So what I want to do first is get this differential equation to be written as a differential form. So what I'm going to do is I'm going to cross multiply here. So the y comes here and the x comes this way. So that now on the left-hand side, what we'll get is the y squared dy. This is equal to x squared dx. So if I integrate both sides, I have y squared dy, integrate x squared dx. So that would actually just come out to be x or y cubed over 3 plus c1. This is equal to x cubed over 3 plus c2. And now I could actually multiply both sides by 3 so that I could get y cubed plus 3c1 equal x cubed plus 3c2. So I'm going to bring the constant to the other side just to make it easier for us. So that means y cubed now is now going to be x cubed plus 3c2 minus 3c1. However, since this constant here is just going to end up with another constant, I'm just going to let c be equal to 3c2 minus 3c1. So that in that case now, what I would just get is y cubed is equal to x cubed plus c. So we don't have to worry about other numbers now, so we could just work on this one here. So and then taking the cube root on both sides, what we'll get is y is equal to the cube root of x cubed plus c. And that is the solution to the differential equation. Now, what do we mean by solution to the differential equation? Well, if we take the derivative on both sides of this function, we should be able to obtain this function that is on the right-hand side. So if I want to show this, try taking the derivative with respect to x on both sides. So I'll get dy over dx, and this is equal to, so I'll write this as, or first, let me write this as y is equal to x cubed plus c to the power 1 over 3. Then if we take the derivative of this, so dy over dx, we get a third times x cubed plus c to the power 1 over 3, or negative 2/3. And so if we simplify things a little, we also have the 3x squared out here. Well, that is going to equal to, so dy over dx, that is equal to, so the 3's will actually end up canceling each other. And what we'll get is, well, x squared will go on the top. And note that, well, we'll get the cube root of x cubed plus c whole thing squared. But note that this part in the denominator, or just this part over here, that is our y. So in the end, what we actually just get is just x squared divided by y squared. So that way we know that we did the differential equation correctly, or solved it correctly. So note that we've seen before that we will have two constants after taking the integral. So we do not want to cancel them out because they might be different constants. They might be the same constants, we don't know. But it's only necessary to have the constant on one side just to make things a lot easier for us. So for example, since I brought the 3c1 to the other side and I let this be a constant, that's going to take more steps. So what I'm going to do is just go ahead and ignore the constant that I obtained on the y and just put it on the right side because it'll end up being a constant regardless. Okay, so sometimes we would like to know what the exact function is supposed to be. So that means we want to have some sort of initial condition in order to obtain the exact function here. So for example, let's say we take the differential equation above, and we want to find an equation that satisfies y0 is equal to 2. So we know that y of x is equal to the cube root of x cubed plus c. However, when y0 is equal to 2, then what I get is just 2, the cube root of 0 cubed plus c, or that's going to be c, the cube root of c. And then if I take the cube on both sides, I would just get c is equal to 8. So that means the exact expression or exact function that we'll get is going to be y of x is the cube root of x cubed plus 8. And this is the exact formula that we would like to sometimes get. So this type of problem here is called an initial value problem, because you have some initial conditions where you actually want to find the exact function. So let's have a look at some more examples. So let's say we want to solve the following differential equations. So for the first one, we have dy over dx, which is equal to 6x squared divided by 2y plus cos of y. Now, obviously, this doesn't look too complicated, because if we cross multiply like we did before, so that way we have 2y plus cos of y times dy this is equal to 6x squared times dx. So now we have an equation in differential form. And so now we want to integrate both sides. So integrate 2y plus cos of y. So whole thing bracket dy. And this is equal to the integral 6x squared dx. So once again, I'm just going to keep the constant on the right-hand side, not going to put it on the left-hand side. But what we'll see that we'll get is that we'll get here y squared plus sine of y. And that is equal to 2x cubed plus c. Now this is probably at most that we could actually simplify here. So I'm going to keep this as a note. So note here, we can leave the answer in implicit form. So this is a function that is implicit. If the equation, or if the solution is implicit. Meaning that, well, because the sine y here, it's going to be a bit challenging as well with this y over here. It's going to be challenging to actually find the direct formula for y. So we're just going to leave it as is. That's okay. All right. So now let's say we want to solve, well, y prime is equal to x squared y. Okay. So let's say, well, y prime, we know that's also the same as saying dy over dx. And that is equal to x squared times y. And what I'm going to do here is I'm only going to divide both sides by y, but I'm also going to multiply both sides by dx. So that when I do that, I will just get 1 over y dy, and that is equal to x squared dx. Now integrate both sides like we did before, so we get 1 over y dy is equal to x squared dx. And so if we take the integral on both sides, well, on the left-hand side, what we'll just get is ln of y, and that is equal to x cubed over 3 plus c. Okay. So here, I'm also going to solve for y because we could just take the e on both sides. So if I take the e on both sides, then the ln and the e will cancel out. So I will just be left with the y. And that is just going to equal to e x cubed divided by 3 plus c. Or alternatively, because we could also write this as e to the power c, e to the power x cubed over 3. I'm just going to let this be equal to a here. And so the solution, or general solution to the differential equation here, is just going to be x cubed, ax cubed divided by 3. Okay. All right. So sometimes differential equations can also be used for modeling problems. And you'll often see if you're in engineering or chemistry, maybe if you're looking at a population pattern, they will always come up a lot. So let's say that, well, we're going to have a look at a physics problem. So let's say that the current IT is in an electric circuit is given by the differential equation L times di over dt plus Ri equal to Et, where L is the inductance, R is the resistor, E is the voltage. So let's say we want to find the expression for the current in the circuit where the resistance is 12 ohms, the inductance is 4 Henry, a battery gives a constant voltage of 60 volts, and the switch is turned on when t is equal to 0. So we actually have an initial problem here because we're given that, well, the initial time here is 0, so we have to assume that, well, when the time is turned on, that's when the process starts. But when it's at 0, that's when we're saying there's no current going through, right? Okay, so that means, so when t is equal to 0, it means that I0 is equal to 0. Let's start with that. So we're told that the inductance is 4 Henry, the resistance is 12 ohms, and the voltage here, 60 volts. So that means our differential equation then becomes 4 di dt plus 12i, and that is equal to 60. So we have a constant voltage throughout. So that means we could actually rewrite the differential equation as di over dt. So that is equal to 15 minus 3i. And so now we could actually separate the variables once again. So I'm going to divide both sides by 15 minus 3i, multiply both sides by dt. So that means here I have 1 divided by 15 minus 3i di. This is equal to dt. Then I integrate both sides, so I get 1 divided by 15 minus 3i di integral of dt. So now that is, if we take the integral of this is going to be 1 over 3 ln of 15 3i. This is going to be t plus some constant c, which we will have to find later. So if we multiply both sides, what we get is, well, we have ln 15 minus 3i. This is equal to negative 3 t plus c. I'll leave the c because it's still constant. Doesn't really affect here. Okay. And then I take the e on both sides. I will then get, well, 15 minus 3i is equal to, well, I just have e to the power of negative 3t plus c, but I could also write this as a e negative 3t. So solving for I now, I could just get I, which is equal to 5 minus a divided by 3 e to the power of negative 3t. So applying the initial value that I0 is equal to 0. So when I0 is equal to 0, then if we substitute that in, if we find a, so I0 is equal to 0, meaning that, well, 5 minus a divided by 3, e to the power of negative 3 times 0, which is still going to be 1. So this is going to be a is equal to 15. So when a is equal to 15, then the current is going to be given by 5 subtract 5 e to the power of 3t. And that is the formula for the current that is passing through the circuit. Okay, so that's good. So we had a look at the initial value problem. We had a look at the differential equations. So now let's have a look at the next concept, which is called the linear differential equations. So a first order linear differential equation is one that can be put into the form dy over dx plus px times y, which is equal to qx. It turns out that every first order differential equation can be solved when multiplying by an integrating factor, which we will call mu of x. So let's say when we multiply the above equation by mu of x, what we get is that, well, we have mu x dy over dx or let me put this. So bracket, we have dy dx plus pxy. That is equal to mu x qx. So if we can find a mu such that, well, what we actually want is that this equation here will actually be able to satisfy this equation here. So if we can find such a mu, then it should be the case that, well, the mu of xy prime is equal to mu of x, q of x. So that's what we want to try and find here. All right. So now if we integrate both sides, what we'll get is that, well, if we see the integral and the derivative x, y prime dx mu x qx dx, on the left-hand side, we see that, well, the derivative and the integral will actually end up canceling out each other. So that means mu of x, y, is just going to be the integral of mu x qx dx. So then the solution would be given by yx, which is equal to 1 divided by mu of x, the integral of mu x times q of x dx. So to find such an integrating factor here, so now we want to find out what that mu is. So expand the above equation. So we're going to expand this part here so that, well, first let's see what we get. So we have mu x, or mu xy prime, plus the mu x px y. This is equal to, we know that that's going to be equal to mu x y prime. But what is that? We have a product of two functions of x, so that's going to give us the idea that we need to use the product rule. So this side here is where we use the product rule. Okay, so if we use the product rule, because they're both functions of x, so that means we would just have the mu of prime of x, y prime of x, or no, the prime should be on the outside here. Yep, so we have mu prime y plus mu x y prime. So we could see now we have some cancellations. So we had the mu x y prime cancel with this. So what we're left with is now mu x px y, which is equal to mu prime x y. So the y's then will just cancel out each other. And so what we will just get is this bunch over here. So this part is what we're going to be looking at. So now we have a separable differential equation. Why? Well, we want to solve for mu here. So we put this into differential form. So what I'm going to do is divide both sides by mu of x. So that on one side, what we'll get is that, well, the integral of 1 divided by mu of x dx, or d mu. So I'll write this carefully. So what we have is mu x px. So that's on the left-hand side. The right-hand side, we have d mu over dx. So that's what we could do now. So the px dx, I'm going to put on one side, and then 1 over mu du, I'm going to put on the other side. So that is px dx. And so now I'm going to integrate both sides. D mu, which is equal to the integral of px dx. And so that would turn out to be, well, the ln of u, or ln of mu, which is equal to the integral of px dx. So that means mu is just going to be equal to a e to the power px dx. But where's the constant? You may ask, well, the a, we might as well just let this be equal to 0. So I'm going to put this as another note here. So note, here, we let a be equal to 1, just to make things easier for simplicity. So our integrating factor becomes mu of x, which is equal to e to the power of the integral of px dx. Okay. So let me put this on another sheet of paper. So when mu of x becomes e to the power px, the integral of px dx, then if we substitute that back into the differential equation, so the solution to the differential equation, so I'm gonna write down the solution. So what we have is y of x, which is equal to 1 divided by mu of x, the integral of mu x qx dx. So because mu of x is equal to e to the power px dx, or of the integral of that, so if we do the substitution, we get this part times the integral of e of to the power of the integral of px dx qx dx. And if we rewrite this, we would get e to the power negative px dx of this integral times the integral e to the power of the integral of px dx times q of x dx. So what I'm going to do here now, I'm actually going to add an extra constant out here just because we'll end up getting a constant anyways if we take the integral from this. So to save some work, we could just worry about the indefinite integral and not worry much about the constant here. So I'm going to add this here. And that, in fact, is the general solution of a linear differential equation. So this is the general solution of a linear first order, so this is also important, first order differential equation. Good. So that is the general method of solving a linear differential equation. You might see in some textbooks that they would say that, well, you should not memorize this solution. You should actually go ahead and try to work your way through the whole thing. I pretty much disagree with that most of the time because I would like to go ahead and use this formula right away. It's sometimes a lot quicker that way as well. So let's have a look at an example where one I will use, won't use this formula up here. And then the other case, I will have a look at the formula. So let's say that we want to solve the differential equation given by dy over dx plus 3x squared y plus 6x squared. So we want to make sure that the differential equation is of this form, which indeed it is. So let's have a look. Our px here, then, is going to be 3x squared. So that means our integrating factor then, our mu, which is our mu of x, as we said, this is equal to the e to the power of the integral of px dx, which is equal to e to the power of the integral of 3x squared dx, but that is just going to be e to the power x cubed. That. No need to worry about the constant up here. It's fine. So multiplying both sides of the differential equation by the integrating factor, what we'll get is that, well, ex cubed dy over dx plus 3x squared ex cubed of y is equal to 6x squared ex cubed. Now the left-hand side becomes the product rule for derivatives. So our product rule will consist of the ex cubed and the y here. So that is going to equal to 6x squared ex cubed. Now integrating both sides with respect to x, so I'm going to take the dx here. So the left-hand side just becomes ex cubed y, because the derivative and integral will cancel out, and hand side. So if we do this by substitution, so if we let u be x cubed, du is 3x squared dx. So that means, well, 2x, 2 du is going to be 6x squared dx then, right? So that means 2, and then we saw the ex cubed here. So if I integrate this, I'll get 2 e to the power of u du, which is the same as saying 2e x cubed. So that's the integral here. On the right-hand side, we'll get 2e x cubed plus c. And so if we divide both sides by e to the power x cubed, then our solution just becomes yx is equal to 2 plus c e to the power negative x cubed. So that is the solution of this differential equation here, right? So that took some steps. But I want to show you the other way where you could just go ahead and substitute into the formula and you will get a direct answer. No need for product rule. You could just go straight into the formula. So let's say we want to solve the above differential equation using this formula up here. That's what we want to do here. So observe that our p of x, so we want a formula that is in the p of x and q of x here. Our differential equation, we have our p of x given by 3x squared. We have our q of x given by 6x squared. So that means if p of x is equal to 3x squared, q of x is equal to 6x squared, then that means if we just go ahead into the formula, y is equal to e to the power negative of the integral 3x squared dx times the integral of qx. So I'm going to put the 6x squared in front, makes it easier. E to the power of the integral of 3x squared dx plus c. C or beta, it's okay. So if we compute the integrals of the exponents, what we'll get is e to the power negative x cubed times the integral of 6x squared ex cubed dx plus c. And since we have already computed this integral, it's just going to be 2 ex cubed plus c. And so we just get 2 plus ce negative x cubed. So we do end up getting the same solution here. So pretty much it is up to you which formula you would want to use here. Okay. So that is the second section that we will have a look at, but let's have a look at some more examples here before we move on. So let's have a look at x squared plus y prime plus xy, which is equal to 1, but we have the initial value problem that y of 1 is equal to 2. So let's write this into the form p y prime is plus p of x times y, which is equal to q of x. We have to put in the standard form first. Okay, so what we get for the standard form is that we have y prime plus 1 over x y plus 1 over x squared. Or that should be equal 1 over x squared. All right, so now what we get is that, well, our px is equal to 1 over x. Our q of x is equal to 1 over x squared. So let's go ahead and use the formula. It makes easier. So we have y of x, which is equal to e to the power negative of the integral 1 over x dx times the integral of q of x, which is 1 divided by x squared. We have e to the power of the integral 1 over x dx plus c. Okay, so the integral of negative 1 over x is just going to be e to the power negative ln of x. We have the integral of 1 over x squared still, but we still have e to the power ln of x here, dx plus c. Well, e to the power negative ln of x is also the same as saying e to the power ln of 1 over x. But since we're assuming that x is greater than 0, we don't need the absolute value. So the x and the ln, the e and the ln will cancel out each other. So we'll just get 1 over x here. So 1 over x times the integral of 1 over x squared times x dx plus c, 1 over x times the integral of 1 over x dx plus c, and that is equal to 1 over x ln of x plus 1 over x times c. We'll put on top. So solving for the initial value problem, when y1 is equal to 2, so we solve for c. So when it's equal to 1, this is going to be equal to 1. The ln of 1, so that's actually going to end up being 0. And then we still have a 1 here. This is equal to 2, so that means our value c is then going to equal to 2 here. So we have the differential equation. So we have 1 over x is equal to 1 over x ln of x plus 2 over x. And that is the solution. Okay, so let's have a look at the next part. But I'm actually going to be changing one value here because it will get a bit too hard for if we let it equal to 1. So let's say instead we're going to let the 1 be the x here, and you'll see why. Well, if p of x then is our 2x, qx is x, then that means our solution would just be given by yx e to the power negative integral of 2x dx times the integral of x e integral of 2x dx of dx here plus c.
this would just be equal to e to the power negative x squared integral of x e x squared dx plus c. This side we get e negative x squared times the integral of e x squared divided by 2. If you do this by substitution, you could show that this integral here is equal to this, and then plus c, and then so that just means that the solution is going to equal to half plus c e x squared, negative x squared. Okay, so that is actually where I'm going to wrap things up for this lesson here. So the next lesson will actually be having a look at two more concepts in differential equations, which I do think is important. And that is going to be talking about the reduction of order. And we're also going to be having a look at the homogeneous equations here. So we had a look at two concepts, separable and linear differential equations. Those are going to be the ones that are the primary concepts of first order differential equations. So if you have any questions, just feel free to let me know in the comments down below, and I will see you guys in the next video.